So now in this video, by now you should have looked into the general proofs and also the first video where we talked about all of the proofs with their descriptions, definitions, and we also gave a real life example to understand it. Now, after that, we then talked about the different types of numbers and the names that are used to describe these different types of numbers. And we do see it in this question I'm going to do in a second. And we also looked at symbols because some questions we need to know their symbol notation for describing a type of number. So now with this method where we're going to be using exhaustion, as a quick reminder, but the full video, if you would like to see the description, is that you want to basically use your statement and you want to use all the possible outcomes to test each outcome being true. So we have here that prove by exhaustion that numbers 1 plus 2 plus 3 up to n is equal to n bracket n plus 1 for all values of positive integers from 1 to 6. So these are our positive integers, and we should know by now what a positive integer is. So we want to use numbers 1, 2, 3, 4, 5, 6. And exclusive means we're going to include 1 and 6. Now, we want to prove using this formula. So it says 1 plus 2 plus 3 plus up to n is equal to n bracket n plus 1 over 2. So what this means is, for each number, if I want to prove it when n is 1, n is 2, 3, so I want to basically prove that 1 is going to equal to n bracket n plus 1 over 2. But now, if I was to take my sums of 1 and 2, I want to show that that's going to equal to n bracket n plus 1 over 2. So let's do this. So when n is 1, this is the first case, and I want to prove that it's true. So it's equal. So n is 1. I want to show this is going to equal to n bracket n plus 1 over 2. So this is what I'm trying to prove. So n is 1. So I want to try and prove this. So I'm going to sub 1 into the left-hand side. So I'm going to have 1, which is already there. And it's equal to 1 bracket 1 plus 1 over 2. And I'm going to be left with 1 times 2 over 2. And that gives me 1. So yeah, 1 is equal to 1. Now, when I want to count my numbers up to 2, so n is going to be equal to 1 plus 2 on the left-hand side. Now, I want to find out if this is going to give me n bracket n plus 1 over 2 is going to give me the sum of 1 plus 2. So I know for sure this is going to give me 3. So I'm going to have 3 is equal to, now because I'm doing up to the sum of when n is 2, so I'm going to sub in 2 bracket 2 plus 1 over 2. And then now if I was to simplify the right-hand side, so I know the left-hand side is 3, but I'd like to get 3 on the opposite side. So 2 times 3 over 2. And yes, I get 3. So I've proved it when n is 1. Now when n is 1 plus 2, and I'm using the largest number, which is 2, I'm going to continue. And I want to now use when n goes up to 3, so 1 plus 2 plus 3. And you can see how we use exhaustion. We have to try every single individual scenario and show that for each case that is true in accordance to the general statement. So when n is going to be up to 3, so n is going to be 1 plus 2 plus 3. And I know that's going to give me, let me rewrite this again. So n is equal to 1 plus 2 plus 3. So this is going to equal to 6. So I would like to try and see if I can get 6 on both sides. So the maximum number I'm using is 3. So 3 bracket 3 plus 1 over 2. So that's going to give me 3 times 4 over 2. And that equals 6. So yeah. So when n is 1 plus 2 plus 3, that gives me 6. And also when somebody n is 3, I also get 6. So now I'm going to keep going. And I'm going to do when n is equal to 4. 1 plus 2 plus 3 plus 4. So this is going to equal to 10. Yep, 10. So I want to try and see if I can get 10 on the opposite side by subbing in n is 4. So 10 is going to be equal to 4 bracket 4 plus 1 over 2. And that's going to equal to 4 times 5 over 2. And I'm definitely going to get 10. So you can see now how I use exhaustion. So we have to try all of the possible scenarios individually and show that for each case is true. So that's why it's exhaustion. So this is what it is. So now I have to keep going because I have to stop up to 6 inclusive. So now I've got 2 more to go. So n is 1 plus 2 plus 3 plus 4 plus 5. So when n is up to 5, the total sum is going to be 15. So I would like to now sub in n is 5 this time into this formula. So 15, which I already have, is equal to 5 bracket 5 plus 1 over 2. And we're going to get 15 is equal to 5 times 6 over 2. And yes, I'm going to get 15. So when n is 5, both of my values on the left-hand side and right-hand side are equal. So now let's try when n is 6. So when n is basically up to 6, so numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6, that's going to give me 21. So now I would like to basically find out if I can get 21 on the opposite side by subbing in n is 6 and have bracket 6 plus 1 over 2. And that's going to give me 6 times 7 divided by 2, which is 21. So yeah, so now I've proved for all of my individual cases within my set of values that this statement has given me. For each case, I've shown that this whole general statement is true, and this is by proving it by exhaustion. So even though one can be right or two can be right, we have to show that for all possible scenarios that is true, the general statement, which is 1. So you're going to add up numbers up to where you stop at n is going to equal to the amount of numbers you have, which is for each case you're going to have 1 and then you're going to have 2, because when 1 plus 2 you have 2 numbers, and then you sub it in, and then we have 3 numbers, you sub in 3 and 4 and 5 and 6, and then we want to show that the numbers on both sides equal each other, and we've shown that. So this next question. So it says, prove by exhaustion that if n is a positive integer that is not divisible by 3, then n squared minus 1 is divisible by 3. So in this case now, we're not given a range, but rather we can decide how many times we want to show that no matter what n is, which is a positive integer, and it's not divisible by 3, then if you was to then compute n squared minus 1, it will be divisible by 3. So if we are going to say that n is a positive integer, so it's not divisible by 3, this whole statement, we can say n is going to be 3k, and then we can add a number to 3k. Because 3k itself, this means 3 times any number. So this is going to equal a multiple 3. And any number as a multiple 3 is obviously going to be divisible by 3. So what we want to do is basically add at least 1, you can add 2, but you don't want to add 3, because if you add 3, then it's going to be divisible. So let's actually try this first case. So let's say n is 3k plus 1. Let's sub it into n squared. So sub into n squared minus 1. And this is going to give me 3k plus 1 squared minus 1. I want to show that this is divisible by 3. So let me expand this bracket. So I'm just going to quickly just do it. So it's going to be 9k squared plus 6k plus 1. And then bring the minus 1. And this is going to become 9k squared plus 6k, because the 1 minus 1 goes away. So 9k squared plus 6k. Now, if it's divisible by 3, I want to have a 3 outside by trying to factorize. So if I factorize this, I can definitely have a 3 outside. So I'm going to have 3 bracket 3k squared plus 2k. So now what this means is any any number I have inside of my brackets, the fact I'm going to multiply by 3 is going to be divisible by 3. And now let's try it again. So let's now do it for when we have n is not just 3k, it's 3k plus 2. Because we said if you have n is 3k plus 3, this is going to be divisible by 3. Because let's say k is 1, you're going to have 3. 3 plus 3 is 6. Is a multiple of 3. So any multiple of 3 and you add 3 again, that's going to give you a multiple of 3. So we don't want to add 3. So let's now remove the 3 and let's add a 2. Now we're going to sub in 3k plus 2 into n squared minus 1. And that is going to be 3k plus 2 squared minus 1. And this would equal to, so again, double brackets. We're going to get 9k squared plus 12k plus 4 minus 1. I'm going to get 9k squared plus 12k plus 3. Now I can see here what I do have is, yeah, this is definitely divisible by 3, because if I factorize everything by 3, I'll get 3k squared plus 4k plus 1. So whatever I get inside of my bracket, the fact I'm going to multiply it by 3 is going to be a multiple of 3, and therefore I can divide it by 3, which is divisible. So I have shown by proof by exhaustion that anything from 3k plus 1, 3k plus 2 is going to be not divisible by 3, but when I sub it into n squared minus 1, I'm going to get a expression that is divisible by 3. And the good thing is we don't have to, there's no limit. So I've shown by giving more than one example that I can prove exhaustion. So this is something as well to you could take away, is that if you're given a question you have to prove by exhaustion and you're not told how many times you have to prove it for each case, if you can prove more than once, so twice at least, that the original statement is true, then you use exhaustion, just like in this example. But in the previous example, we had to use the numbers from 1 to 6. So we were given a range of numbers we had to use. So we had to use all of these possible, we had to use these single numbers one by one and prove that the general statement is true for each of these numbers. And that's what we did. So now let's look into the third one. So this third question here. So let's look into this third one, and this is the final one I'll be doing today. So it says if n is a number between 2 and 5. So now we can see we've been given a set of numbers to prove by exhaustion. Then n cubed plus n is or has a factor of 5. True or false? Now, what we have to do is we have to decide if this statement is true or false. So it's different to the previous examples. Now, if you want to find out if it's true or false, we have to use exhaustion to show that if it's going to be true. Because if it's going to be true, then that means our values between 2 and 5, which is going to be 3 and 4, is going to be that when you have n cubed plus n is a factor of 5. And then if not, if we find out that, okay, when you have 3 and 4, if both of them are not a factor of 5, or let's say if one of them end up to not be a factor of 5, then we're going to say this statement is false by exhaustion, because we have a range of numbers. So always remember, if you're given a range of numbers and you have to prove something, then you most likely have to use exhaustion if it's not given to you. But generally speaking, they will tell you which method to use. So let's do this. So if let's say n is 3, I'm going to sub in n cubed. So that's going to be 3 cubed plus n. And I'm going to get, so yeah, n is 3. I'll just put n. So 3 cubed plus 3, that's going to give me 27 plus 3, which is 30. Yes, 30 is a factor of 5. No, 5 is a factor of 30 because it has a factor. Yeah, a factor is a number that you divide by another number to give you a whole number. So yeah, 30 does have a factor of 5. Now let's do when n is 4. Because we want to see if all of these numbers is going to tell us if the statement is true or false. So that's why we're doing exhaustion, because we want to try each possible number within the range that we're given. So 4 is a number between 2 and 5. Bear in mind, it doesn't say inclusive, so we don't have to test for 5 or for 2. So let's do 4 cubed plus 3 plus 4. And I'm going to get 4 cubed is 64. 64 plus 4 is 68. So 68 is not a factor of 5. So therefore, this statement is false. So it's not going to be true. So by exhaustion, we have now seen that this statement, where n is a number between 2 and 5, then n cubed plus n has a factor of 5, is false. So this is false. And by proof of exhaustion, this is false, because we came to realize that when n is 4, the number we get does not have 5 as a factor. So that is it for today with these questions. And if you would like more questions, more practice questions, and also questions where you see them from different exam boards, then in my online portal, you can definitely practice more of those questions. And if you would like to get details for that, you can comment below, or you can check the link on this description, where I'll be providing the link for students to join, and you can access those materials. I'll see you on the next one, where we'll look into proof by counterexample, and then hopefully we'll look into proof by contradiction. And that will be everything in this series. So I'll see you on the next one.